Episode 3. Title of the radio enabled course is Energy Physics. In this episode 3, first of all, we should know about chemical energy sources. These energy sources includes importance of efforts on the development of fuel cell and batteries. The development of particular type of fuel cells and batteries holds promise for running small and light commercial vehicles in the beginning, followed by for heavy vehicles. Rural electrification of remote small villages having population of 100 to 500 through rechargeable power batteries. That means the batteries can be charged with the help of windmills. This would also help achieving the social objectives of the government to provide electricity for lightening rural areas where laying of transmission faces hazards. The work on batteries and fuel cells, vice versa, sodium sulfate batteries, metal air rechargeable cells, hydrogen oxygen and lithium fuel cells, etc. is already in progress in a number of places in our country. The Department of Non-Conventional Energy Sources, that means DNES, India, has been promoting R&D efforts relating to chemical and electrochemical sources of energy, keeping in view their potential role in the long term. The department extended support for studies relating to beta alumina for sodium sulfur batteries, lithium-ion conductors for solid-state batteries, fuel cell materials, and development of high-energy density storage batteries suitable for photovoltaic and other applications. From this general introduction, we move on to fuel cells. A cell, combination of cell, capable of generating an electric current by converting the chemical energy of a fuel directly into electrical energy. The fuel cell is similar to other electric cells in the respect that it consists of positive and negative electrodes with an electrolyte between them. Fuel in a suitable form is supplied to negative electrode and oxygen from air to positive electrode. When the cell operates, the fuel is oxides and chemical reaction provides the energy that is converted into electricity. Fuel cell differ from conventional electric cell in the respect that the active material, that means fuel and oxygen, are not contained within the cell but are supplied from outside. But for its cost, pure, that means fairly pure hydrogen gas would be preferred fuel for fuel cells. Alternatively, impure hydrogen obtained from hydrocarbon fuels such as natural gas or substitute natural gas, that means methane, liquefied petroleum gas, propane and butane or liquid petroleum products can be used in fuel cells. Efforts are being made to develop cells that can use carbon monoxide as the fuel. If they are successful, it should be possible to utilize coal as the primary energy source. Main uses of fuel cell are in power production, automobile vehicle, and in special military use. Next, we will see about design and principle of operation of a fuel cell, that means with special reference to H2O2 cell. As stated, these are electrochemical devices in which the chemical energy of fuel is converted directly into electric energy. The chemical energy is free energy of the reactants used. This conversion takes place at constant temperature and pressure. The basic features of the fuel cell is that the fuel and its oxygen are combined in the form of ions rather than neutral molecules. The first practical fuel cell was demonstrated by Francis T. Bazin and J. C. Faust of Cambridge University in 1959. As per the fuel used, the main type of fuel cells are hydrogen H2 fuel cell, hydrazine N2H4 fuel cell, hydrocarbon fuel cell, and alcohol, that means methanol fuel cell. The operation of the fuel cell can best be described with reference to the specific device. Fuel cell can be adapted to variety of fuels by changing the catalyst. Here, hydrogen oxygen, that means hydrox cell, is described for example. These types of cells are the most efficient and the most of highly developed. The main component of fuel cells are a fuel electrode, that means anode, an oxidant or air electrode, that means cathode, and an electrolyte. These are the main important components of fuel cells. In most of fuel cells, hydrogen, that means pure or impure, is the active material at the negative electrode, and oxygen, that means from the oxygen or air, is active at the positive electrode. Since hydrogen and oxygen are gases, a fuel cell requires a solid electrical conductor to serve as a current conductor or collector and to provide a terminal at each electrode. The solid electrode material is generally porous. Porous nickel electrodes and porous carbon electrodes are generally used in fuel cells for commercial application. Platinum and other precious metals are being used in certain fuel cells which have potential utility in military and space application. The porous electrode has a large number of sites and where the gas, electrolyte and electrode are in contact. The electrochemical reaction occurs at these sites. The reaction are normally very slow and catalyst is included in the electrode to them. The best electrochemical catalysts are finely divided platinum or platinum-like metal deposited on a incorporated with porous electrode material. Since the platinum metals are expensive, other catalysts such as nickel, that means for hydrogen fuel cell, and silver, that means for oxygen fuel cell, are used where possible. The very small catalyst particles provide a large number of active sites at which the electrochemical reaction can take place at a fairly rapid rate. Although the practical fuel cell differ in designing details, the essential principles are the same as indicated by the above discussion. Hydrogen gas is supplied to one electrode and oxygen gas to other electrode. Between the electrode is a layer of electrolyte. Most exciting fuel cells operate at temperature below about 200 degrees Celsius. The electrolyte is then usually an aqueous solution of an alkali or acid. The liquid electrolyte is generally retained in a porous membrane, but it may be free flowing in some cells. Different electric current is drawn from the cell in the usual manner by connecting a load between the electrode terminals. The electrochemical reaction occurring at the electrodes of a hydrogen-oxygen cell may vary with the nature of electrolyte, but basically they follow. At the negative electrode, hydrogen gas H2 is converted into hydrogen ion, that means H+. Hydrogen with a positive electric charge plus an equivalent number of electrons. Thus H2 gives 2H plus 2 electron minus. At this electrode, hydrogen is diffused through the permeable nickel in which is embedded a catalyst. The catalyst enables the hydrogen molecules H2 to be absorbed on the electrode surface as hydrogen atom, which react with the hydraulic ion OH- in the electrolyte to form water. When the cell is operating and producing current, the electrons flow through the external load to the positive electrode. Here they interact with oxygen and water, O2 and H2O, from the electrolyte to form negatively charged hydraulic OH- ion. The hydrogen and hydraulic ion then combine in the electrolyte to produce water. The electrolyte is typically 40% KOH solution because of its high electrical conductivity and its less corrosion than acid. The above discussion, that means H plus OH- gives H2O, that the hydraulic ion produced at one electrode are involved in the reaction at the other. Also, electrons are absorbed from the oxygen electrode and released to the hydrogen electrode. Addition of three foregoing reactions show that when the cell is operating, the overall process is the chemical combination of hydrogen and oxygen, that means gases, to form water, that is H2O plus half of O2 gives H2O. The oxygen and hydrogen are converted to water, which is the waste product of the cell. The reactants are stored outside the cell, no difference from storage battery, and the electrodes and electrolyte are not consumed in the overall process. These property load to the design of convenient small size and long life power units. If the electrodes are on open circuit, the hydrogen electrode accumulates a surface layer negative charges. This attractive potassium ion K plus of the electrolyte providing an electric double layer. Similarly, the loss of electrons from oxygen electrode results in a layer of positive charges, which in turn attracts hydroxyl ions OH- from the electrolyte. This electrical double layer at the electrodes build up until the potential are such that they inhibit only other further reaction between the electrolyte and the fuel gases. This situation is illustrated in the following circuits. That means we can connect the two terminals H2 and O2 through the resistance. The magnitude of this EMF is 1.23 volt at 1 atmosphere and 25 degrees Celsius. If the circuit is closed, the electrons can now leave the electrodes, pass through the connecting circuit to the oxygen electrodes, and take part in the reaction of the chemical reaction as discussed. This movement of electrons constitutes a current passing through an external load. In this way, useful electrical work is obtained directly from the chemical process. Note that the electrons flow is from the hydrogen to the oxygen electrode. Then we move on to hydrogen fuel cells. Hydrox are two types. One is low temperature cell. The electrolyte temperature is 90 degrees Celsius. It is sometimes pressurized but not by a great amount, usually say up to 4 atmospheres. Second one is high pressure cell. Pressure is about 45 atmospheres and temperature up to 300 degrees Celsius. Say a single hydrox fuel cell can produce an EMF of 1.23 volts at 1 atmospheric and 25 degrees Celsius. By connecting a number of cells, it is possible to create useful potential of 100 to 1000 volts and power levels of 1 kilowatt to 100 megawatt nearly. The current depends upon the physical size of the cell. The output of the cell varies directly with the pressure. So as to increase the cell output, the gas pressure is raised. The optimum size of the cell at present is about 0.27 cum per kW. The gases in the hydrogen-oxygen cell must be free from carbon dioxide because this gas can combine with potassium hydroxide electrolyte to form potassium carbonate. If this occurs, the electric resistance of the cell is increased and its output voltage is decreased. Consequently, when air is used to supply the required oxygen, carbon dioxide must first be removed by scrubbing with an alkaline medium, that means lime. Fuel cells are particularly suited for low voltage and high current application. Hydrogen oxygen fuel cells have been proposed for application of electric vehicles with the hydrogen provided by a metal hydride. However, this is used very limited by the heavy weighted of hydride and the cost of relatively pure hydrogen required. It appears that for the present, at least the use of hydrogen oxygen cells will be restricted mainly to manned space vehicles. Such cells with porous nickel electrodes and potassium hydroxide electrolyte have been used to provide electric power for the Apollo and shuttle spacecraft. The hydrogen and oxygen for operating the cell are stored in liquid form to minimize the volume occupied. Then now we can classify the fuel cells. Before describing the different types of fuel cells, it is necessary to have some method to classify of various types of fuel cell which are either in existence or being invented. Several methods of classification of fuel cells have appeared in this topic in this episode. One of the difficulties in arriving the systematic classification is that several operational variables exist. For example, fuel cells may classified accordingly to temperature range in which they operate. Low temperature, that means 25 degree to 100 degree Celsius. Medium temperature, 100 degree to 500 degree Celsius. High temperature, that means 500 to 1000 degrees Celsius. At very high temperature, above 1000 degrees Celsius. Another method would be accordingly to type of electrolyte, example aqueous, non-aqueous, molten or solid. One could also classify the fuel cells according to the physical state of the fuel cell. Gas, hydrogen, lower hydrocarbon, liquid alcohols, hydrazine, higher hydrocarbons, solid metals, etc. In the present discussion, a broad division is first made according to whether the fuel cell systems is primary or secondary one. A primary fuel cell may be defined as one in which the reactants are passed through the cell only once, the products of the reaction being discarded. Example, H2O2 fuel cell. A secondary fuel cell is one in which the reactants are passed through the cell many times because they are regenerated from the products by thermal, electrical, photochemical methods. Example, nitric oxide chlorine fuel cell. Then we can say the fuel cell mostly used in hydrogen, fossil fuel, hydrocarbon fuel cell, alcohol fuel cell, hydrogen fuel cell. First we discuss hydrogen oxygen, that means H2O2. The hydrogen oxygen cell of primary system is already described using 40% KOH solution as electrolyte. Here now ion exchange membranes cell will describe which uses membranes electrolyte. Ion exchange membrane cell, the basic design of the cell, which consists of solid electrolyte ion exchange membranes, electrolytes and gas feed tubes is represented. The membranes is non-permeable to the reactant gas hydrogen and oxygen, which thus prevents them from coming into contact. The membranes is however permeable to hydrogen ion, which are the current carriers in the electrolyte. The desired properties of an ideal ion exchange membranes electrolyte are high ionic conductivity, zero electronic conductivity, low permeability of fuel and oxidant, low degree of electroosmosis, high resistance to dehydration, high resistance to its oxidation and hydrolysis, and finally mechanical stability. Next we move on to molten carbonate cells. These are high temperature fuel cells with the molten carbonate mixture as the electrolyte, offer the prospect for use with variety of fossil fuels including coal. A special feature of these cells is that during operating they can oxidize carbon monoxide to carbon dioxide as well as hydrogen to water. Hence gaseous mixture of hydrogen and carbon monoxide, which are relatively inexpensive to manufacture, can be used in the cell. The presence of carbon dioxide would have only a minor effect. Several methods are available for fuel processing. These methods are essentially the same as those used for the commercial production. A mixture of hydrogen and carbon monoxide known as synthesis gas. Synthesis gas can be made from coal by reaction with air and steam or from various petroleum products. In order to prevent poisoning of electrodes in the fuel cell, the gas mixture must be desulfurized before being supplied to the power section. The electrolyte in the high temperature fuel cell under development is molten mixture of alkali metal, that means lithium, sodium, potassium, carbonates at a temperature of 600 degrees Celsius to 700 degrees Celsius. This is retained in an inert porous matrix sandwiched between two porous nickel electrodes. Because of the high temperature, electrochemical catalysts are not necessary on the electrodes. The mixture of hydrogen and carbon monoxide is supplied to the negative electrode and oxygen to the positive electrode. The discharge EMF of the cell is about 0.8 volt. The electrolyte is usually held in a sponge like ceramic matrix. Metallic electrodes are placed in direct contact with solid electrolyte. The hydrocarbon fuel such as methane, kerosene is used. The fuel is reacted inside the cell to produce H2 and CO. At the fuel electrolyte, H2 and CO react with CO3 ion in the electrolyte, releasing electrons to the electrode and forming H2O and CO2. At the oxygen electrode, O2 reacts with the returning electrons and CO2. An important aspect of the molten carbonate fuel cells is that the discharged gas, consisting mainly of the steam, carbon dioxide products and nitrogen from the air, are at a temperature exceeding at 540 degrees Celsius. The hot gas could be used to provide industrial process heat to operate a gas turbine or to produce steam in a waste heat, that means heat exchanger boiler, to drive a steam turbine. The turbine would be attached to a generator to produce additional electric power. The overall efficiency for fuel use would thus substantially increased. Another important types of fuel cells are solid oxide electrolyte cells, aluminum oxygen, that means air cells, photochemical regenerative fuel cells, regenerative systems. These are the other important types of fuel cells. Then we will discuss about advantages and disadvantages of fuel cells. First, advantages. It has very high conversion efficiency, as high as 70% have been observed, since it is direct conversion process and does not involve a thermal process. In the conventional thermal process for generating electricity, heating energy produced by combination of the fuel is converted partially into mechanical energy in a steam turbine and then into electricity by means of a generator. The efficiency of a heat engine is limited by the operating temperature, and in the large modern steam electric plants, above 40% of the heat energy of the fuel cell is converted into electrical energy. Fuel cells, on the other hand, are not heat engines and are not subjected to their temperature limitations. Second advantage, fuel cells can be installed near the use point, reducing electrical transmission requirements and accompanying losses. Consequently, considerably high efficiencies are possible. Third advantage is they have few mechanical components, hence they operate fairly quietly and require little attention and less maintenance. Then fourth advantage is atmospheric pollution is small. If the primary energy source is hydrogen, the only waste product is water. If the source is the hydrocarbon, carbon dioxide is also produced. Nitrogen oxides, such as a combination of fossil fuels in the air, are not formed in the fuel cell. Some heat is generated by a fuel cell, but it can be dissipated to the atmosphere or possible use locally. There is no requirement for large volumes of cooling water, such as necessary condensed exhaust system from a turbine in conventional power plant. Next important advantage is, as fuel cells do not make noise, they can be readily accepted in residential area. Another important advantage is the fuel cell takes little time to go into operation. The space requirement for fuel cell power plant is considerably less as compared to conventional power plants. The major disadvantage, the major drawback is the main disadvantage of a fuel cell are their high initial cost and low surface life. That is the most important drawbacks in real-time application for domestic purpose and also the industrial purpose. Dear student, in this episode 3, we discussed about energy from chemical sources. We will discuss about next topic in episode 4. Thank you.